In this video we're just going to look at one extra particle or one new particle that you've seen mentioned before but we haven't really talked about it, called the neutrino. And really this is kind of like a little bit of a history lesson more than anything else, just based on where the neutrino came from and what a neutrino is. So you might remember back when we did nuclear physics and nuclear decay, one of the types of nuclear emissions was beta emissions. And in beta emissions, what happens is a neutron in the nucleus is converted or changes into a proton and an electron. And the electron is emitted, it's kicked out of the nucleus, and then you have an extra proton in the nucleus. So there's one less neutron and one more proton. But the overall mass number will stay the same because one neutron has been converted into a proton. Now there's another way you could write this, and you've seen this written a few ways. You could write it as H11, and you could also write it as beta minus 10. So this is known as beta decay, and this is the beta decay equation, which you should know and be familiar with already. Now, scientists were looking at this. They were looking at this equation, and they were researching it, and they wanted to check that it follows all the laws. And remember, there's 3 conservation laws that you need to remember. And one of them is charge. So is the charge before the reaction happens, I suppose, the same as after? And if we look, the charge of a neutron is neutral, or 0. The charge of a proton is +1. And the charge of an electron is -1. So overall, that's a neutral charge. So yeah, charge is conserved. The next thing they wanted to check if it was conserved was energy mass. So basically they look at how much energy is here using E equals mc squared, how much energy is here using E equals mc squared, and maybe if there's kinetic energy involved as well. And when they looked at it, that looked fairly okay. Now they weren't exactly the same, but as you know, in science and any experiments, there's always a little bit of an uncertainty. So you might have a small difference, but you can usually put that down to experimental error. Then they looked at momentum. And when they looked at momentum, they found that actually momentum wasn't conserved. The momentum before was not equal to the momentum after. So the guy who saw this, or who noticed this, was a guy called Wolfgang Pauli. I'm going to write his name here, just make sure I have the spelling correct. Do I have the spelling correct? Pauli, anyway. P-A-U, I think it was Wolfgang Pauli. And when Wolfgang Pauli was looking at that, that's terrible writing. Hang on, I'm going to get rid of that. Wolfgang Pauli. And when Wolfgang Pauli was looking at this, he said, well, this doesn't make sense. It can't be right that momentum isn't conserved, because that's one of our laws. That's one of the things we have to make sure is conserved. So what he actually did was he says, well, in order to make momentum be conserved, I need to add in another particle. I need to add in an extra particle here that we just can't see, we just can't detect. And he gave that particle the symbol V like this, and he called it the neutrino. And he called it the neutrino for 2 reasons. One, because he said it's so hard to detect, it must be neutral. Because things which have a charge are generally easier to detect. And the second reason he called it neutrino is because the neutrino stands for that it's very, very, very small. So basically he predicted this particle, the neutrino, that is neutral and very, very small, which means it has a very small mass. And those 2 facts, the fact that it's neutral and the fact that it has a really low mass, means that it's really, really hard to detect. And it wasn't until years later that they actually detected it, but the equation then becomes, we have a neutrino goes to a proton and an electron plus a neutrino. So this neutrino is now included in that equation as the particle that makes it possible for momentum to be conserved. And that's really all you need to know about the neutrino. You need to know this equation. you need to know that it's very small and it's very hard to detect and it has a neutral charge. Now there's three different types of neutrinos. There's the electron neutrino, and this was all discovered over years and years. The electron neutrino, and these are all fundamental particles, part of our standard model. There's the tau neutrino, and there's the muon neutrino. And of course, for each one of these, there's an antiparticle as well. So that's 6 more fundamental particles. So you have the electron neutrino, tau neutrino, muon neutrino, and then you have the antiparticles as well. Last thing, for the antiparticle, if this is the symbol for an electron neutrino, the symbol for an anti-electron neutrino, as I just said, is this. Sorry, I've said that already. Okay, so that's basically all you need to know with it. You just need to make sure you learn it, and I'll give you a question which kind of asks a little bit about neutrinos so you get a feel for what they kind of tend to ask with this.